My name is Ben Cohen, and I'm here to present on planning single-arm manipulations with N-arm robots. This is joint work with my lab mate, Mike Phillips, and our advisor, Max Likachev. I'm from UPenn, and they're from CMU. So in most of our research labs, we have a single arm because they're really expensive. But actually, in the wild, naturally, arms are found in herds, okay? On the floor of a factory, you'll find hundreds of arms. And even in home robotics too, right? We keep designing our Rosies from the Jetsons with 2 arms, not 1. And in most of these cases, you have arms that actually share workspaces with each other. So if you just gave these arms the ability to hand up an object between each other, now the workspace of a single arm becomes that of the entire set of arms. And also, your arm can now regrasp an object with a handoff instead of a slow put down and pick up. So the goal here is to come up with a motion planner capable of planning the motion for the arm or arms required to move an object from point A to point B. And for that, the planner has to reason about a whole bunch of stuff that we'll talk about. Okay? But in motion planning, we want our planner to be fast, right? So for this, one of our goals is we want the planner to be fast. We also want to generate high-quality solutions. And we also want the planner to be consistent. Okay? And by that I mean, given similar input, you get similar output. And why is that important? Because we keep talking about human-robot collaboration. And now I'm a factory worker, right? And I'm working near a robotic arm, no more cage, okay? So I know the task it's doing. I want to be able to safely predict how it's going to do it, okay? So here we have an example of this futuristic bar. We want to move this tray from the left side of the bar to the right. In pink, we see the initial pose. In green, we see the goal pose. And it must be happy hour. We have a lot of bartenders. We have 3 arms working this bar, okay? So the planner will decide, is 1 arm needed, or is all 3 needed, or is 2 needed? The planner will make that decision. Also, we have a set of pre-computed grasps for this object that the planner could use. So the goal is to find a path from that pink pose to the green pose, and this problem is really interesting, right? Because we actually have discrete components and continuous components. We have to figure out the arm and grasp for the object pickup and the put down, and about the handoffs. Do we need a handoff? And for each handoff, who, what, where, when, and why? And now, the continuous side, we have to figure out that 6-stuff motion that the object is going to take from the start to the goal, and the joint space trajectory from the start for each support arm along the way. And now this is the solution that we planned. And this video is really boring. It's boring because it does exactly what you'd expect it to do. The near arm to the start picks it up, gives it to the middle arm gives it to the third arm, it's closest to the goal, third arm puts it at the goal. It took like 6.5 seconds to plan this path. This one is a little bit more interesting, same start pose, but the goal pose is now underneath the bar. And you saw our pre-computed set of grasps. Only one of them is valid here. So the planner, when it's figuring out the details of the second handoff, is going to have to reason about the second arm has to give it to the third arm such that the third arm can grasp it with that grasp so that the goal is feasible. And this took about 8 seconds to plan. So for our approach, we use the search-based planner, weighted A*, because combinatorial searches are really good at handling problems with discrete and continuous components to them. We also used it because 2 of our goals are consistency and high-quality solutions, and search-based planners will give you that. But our third goal is we want the planner to be fast, okay? And we know that in high-dimensional spaces, search-based planners tend to slow down, right? So we had to come up with these components to deal with that. And the first one is we use a lazy version of weighted A*. With it, we get the same performance boost that you get with weighted A* and all of its theoretical guarantees. But now we could postpone the expensive evaluation of edges until the search realizes that those edges are needed to find the solution. And now we're doing handoffs here. So you can imagine that we're going to have to call a single arm path planner many times during the search. It could get expensive. So now we have a really efficient search, but we have a huge configuration space. So for that, we had to come up with a compact graph representation, and we did. And it's nice. It scales well with the number of arms, okay? And all these arms could be different, and they could all have different kinematics. And you could have a KUKA, hand something off to a Motoman, we can make peace. They could all be different, okay? Also, our graph representation is nice because it supports regrasping. But now we have a compact graph and a fast search. But your A* variants are only good if you have a good heuristic. And like I said before, we have these 2 sub-problems. So we had to come up with 2 heuristics that we combine to deal with both of them. And the first one helps the object guides the object around obstacles from the start to the goal. And the second one, it helps the planner reason about which arm and grasp to use at which time, and also minimize the number of handoffs. So we have experimental results for 2, 3, and 4 arms. We have a comparison to another planner. We also have a whole lot of video in different scenarios, including a factory scenario. So if you're interested in the details, stop by the poster tomorrow morning. Thank you.